Take a look at this scene. What do you see? If you're a speaker of a natural human language, your answer is probably a fish and a tree. But why do we split this scene into two different objects, and why specifically these two? Theoretically, there could be a language with a single word, a single morpheme that refers to this thing as a whole. There could also be another language that splits this scene into two objects, one that we will call a fish head and tree branches, and the other we will call the body of a fish and a tree trunk. But natural languages don't do this because humans don't think of the world this way. For humans, a fish is more of a singular concept than whatever this is.
Natural human languages come with all kinds of phonology, morphology, and syntax.
But they all probably have one thing in common. Natural languages generally have content words that map decently well to the speaker's mental model of the world. I'll call this principle the mental model principle. But what if we try to break this principle? What if we made a language where singular human concepts are diffused across entire sentences? And what if we did it using linear algebra and modular arithmetic?
Hi, I'm Kat, and this is Goptjaam.
So, where do we start? We want to map human concepts to something that's diffused across the entire utterance, and we can do this mathematically using linear algebra. The basic idea is that we map each concept to an infinitely long vector, and each component of the vector corresponds to a position in the sentence. Then, to add more concepts to the sentence, we simply add up their vectors to get the final sentence vector. Each number in the sentence vector is then mapped to a syllable in our Conlang. This way, if we add or remove a concept from the sentence, or swap out a concept for another, it would have an effect on the sounds throughout the entire sentence. Did I say infinitely long vector? Yes, I did. In order for us to be able to convey an arbitrary amount of information and make arbitrarily long sentences in the language, the vectors cannot be finitely long. But it's kinda difficult to pronounce infinitely long utterances, so we truncate it at the point where pronouncing more syllables conveys no more information. To spoil things mildly, it turns out that this can be done, and we will explore this later in the video. Since there are only finitely many possible syllables, there should only be finitely many possible numbers in each vector component. Because of this, we will use modular arithmetic for adding up vectors. What this means is that we will constrain the vector components to be integers that are at least 0 but less than some positive integer p. And these numbers wrap around, like on a clock, so the number after p minus 1 is not p, but 0. There is, however, a subtle problem with what we have so far. Our Conlang cannot convey information about the relationships between concepts. What I mean is this. If we want to express the cat eats the fish, the sentence vector would be the sum of the vectors of the concepts cat, eating, and fish. But this is the same sentence vector as the one for the fish eats the cat. They involve the same three concepts, and because addition is commutative and associative, the sentence vectors end up the same. So how do we know whether it is the cat or the fish that is doing the eating? There are a few ways natural human languages deal with this problem. English and Hokkien, for example, often use word order to convey this information. We have the cat eats the fish versus the fish eats the cat, and niaoa de jia hia versus hia de jia niaoa. Some languages like Japanese use small words called particles that attach to content words to convey this information. For example, neko ga sakana o tabeteru versus neko o sakana ga tabeteru. The particles ga and o mark the subject and object respectively. Other languages modify the content words themselves to convey their relationships. Latin does this, for example, fe les piscem comedit versus fe lem piscis comedit. Most English pronouns also do this. The different possible inflections of the word are called cases. In our Conlang, because there's no way for us to order the concepts in a sentence, it is impossible to use word order to convey the relationship between concepts. Adding particles is also not possible because there's no way to know which particle goes with which concept in the sentence. So that leaves us with modifying the concept vectors themselves. What we'll do is, instead of mapping each concept to a vector, we'll map each concept case pair to a different infinite vector. And the case can be any positive integer. That's right, our Conlang has infinitely many cases. Looking at this from a different perspective, it is equivalent to saying that each concept in our cursed Conlang has associated with it an infinite 2D matrix, where the ith column of the matrix is the vector associated with the ith case of the concept. But actually, we can simplify this. Instead of having to come up with a unique matrix for each concept, we can simply have one infinite matrix, which I'll call the base matrix. Matrices for different concepts will then be different multiples of this base matrix. Each concept is assigned a positive integer between 0 and p-1, and this concept number is multiplied with the base matrix to get the matrix for the concept. This simplification comes with a limitation. No two concepts can have the same case within the same utterance. Suppose we have a sentence that consists of just concept 4 in case 2. The sentence is then simply 4 times the base vector for case 2. But we can also get the same sentence by adding concept 3 in case 2 with concept 1 in case 2, or even twice concept 2 in case 2. As we can see, there will be a lot of ambiguity if we allow for multiple concepts to have the same case, so we prohibit this. To summarize what we have come up with so far, we have an infinite base matrix, and the vectors of each concept case pair is a multiple of a column of this base matrix. Then to construct a sentence, we add up the concept case vectors that make up the sentence, and the vector we get we can convert into syllables to make it pronounceable. You might recognize that this is simply matrix vector multiplication. We can represent the concepts and cases that make up the sentence using an infinitely long vector, where each entry corresponds to a different case. We'll call this vector the summary vector, since it summarizes the entire utterance. Note that the summary vector is fundamentally different from the concept case vectors, so to differentiate them, I'll always write the summary vector in purple. If we want to construct a sentence consisting of concept 3 in case 1 and concept 4 in case 2, we make the first component of the vector have a value of 3, and the second component have a value of 4, and all other components are 0. If we then multiply this infinite vector with the base matrix, the first column of the base matrix is multiplied by 3, and the second column is multiplied by 4, and these are added up. All the other columns are multiplied by 0, so they don't contribute to the sum. This sum is then exactly the sentence vector. We have just written the procedure in a more mathematical form. So now that's left is to construct the infinite base matrix, but it can't just be any infinite matrix. Remember, we had a condition the base matrix has to be able to meet. How do we guarantee that the listener can always unambiguously figure out which concepts and cases make up the sentence? And how do we choose a cutoff point for this sentence such that that is guaranteed? Because we have translated our linguistic problem into the language of linear algebra, we actually have tools to tackle these problems. In linear algebra terms, how do we truncate the infinite base matrix into a finitely sized matrix such that the truncated matrix is invertible? These questions are not only relevant to constructing our cursed Conlang, but also to the field of cryptography. The method we are using to convert from concepts and cases to syllables is exactly the same as a cipher called the Hill cipher. Also, I've used the term diffuse a few times so far, but it has a special meaning in the field of cryptography. If we change any entry of the input, then it should have an effect on most of the entries of the output. This is also called the avalanche effect. A related concept in cryptography is confusion, which is when each entry of the output depends on several entries of the input. In fact, the Hill cipher and our cursed Conlang have both of these properties, provided that the base matrix is dense, meaning that it has very few zeros. Unfortunately, the Hill cipher is not used anymore by itself, but some modern ciphers still use matrix multiplication in order to achieve diffusion of the input, which means that in fact, there is some real-world use of solving this mathematical problem other than making this cursed Conlang. So without further ado, let's actually try solving it. The following two sections of the video will be more mathematical and will assume some basic knowledge of linear algebra. If at any point you feel like you're lost, or if you're just here for the funny conlanging, you can skip directly to the actually constructing the language section and you'll be fine. But if you want to dive into the maths, that's great. Let's continue. So, invertible matrices. What invertible means is that you can find another matrix whose matrix multiplication undoes the matrix multiplication of your original matrix. One of the first things you learn in an introductory linear algebra course is that a matrix is invertible if only if it is square and all of its columns are linearly independent. Thus, we will truncate the base matrix to just the top left n by n submatrix, where n is the largest case used in the sentence. Furthermore, the condition that the columns have to be linearly independent is in fact not very strict at all. Most square matrices have linearly independent columns. So now, we just have to find an infinite linearly independent matrix, right? But here's the catch. The results you learn in your average linear algebra course assume that you're dealing with arithmetic involving real or complex numbers. Here, however, we're doing modular arithmetic on integers, so do the results regarding invertible matrices generalize to modular arithmetic? The answer is yes, but only if the modulus p is a prime number. The reason that we're able to generalize these linear algebra results is that these results were not proven just for the case of real and complex numbers. Rather, they were proven for more abstract algebraic structures called fields and vector spaces. The definitions of these fields and vector spaces consist of only the bare-bone properties that make the theory of linear algebra and other branches of mathematics work. For example, fields are an abstract generalization of the real numbers and the complex numbers. A mathematical object is a field if it has the following properties. Addition and multiplication are defined and have the properties of commutativity, associativity, and distributivity. Commutativity for addition means that a plus b is equal to b plus a. Associativity means that if we have a plus b plus c, then adding a and b first will result in the same number as adding b and c first. Furthermore, addition and multiplication both have to have an identity element. For the real numbers, these are 0 and 1 respectively. We're adding a number with the additive identity and multiplying a number with the multiplicative identity both result in the original number itself. And lastly, each element of the field has an additive inverse. For the real numbers, the additive inverse of a number is negative. And each element except for the additive identity, 0, has a multiplicative inverse. For the real numbers, this is 1 over the number. It's not hard to show that real numbers and complex numbers satisfy these properties, and so are fields. And so any result that has been proven involving fields also applies to the real numbers and the complex numbers. As for vector spaces, they're the abstract generalization of all of these arrays of numbers that we've been calling vectors so far. By its definition, it must have a field associated with it, with addition defined between vectors, as well as multiplication between vectors and elements of the field, with similar properties to those of fields. So because of this generalization, we just need modular arithmetic over integers to be a field for the results from linear algebra to apply to what we're doing. And it turns out that modular arithmetic over the integers forms a field if and only if the modulus p is a prime number. The reason for this is that if p is not prime, it has some factor k that is not 1 over itself, then k does not have a multiplicative inverse. To have a multiplicative inverse, there must be some integer that you can multiply by k to get 1 plus a multiple of p. But p divides by k cleanly, so 1 plus any multiple of p divided by k will always leave a remainder of 1. Therefore, k does not have a multiplicative inverse, and so the integer's modulo p is not a field if p is not prime. This problem does not occur if p is prime, and you can show that in this case it is indeed a field. What all of this means is that as long as we choose a prime number for p and the base matrix is always invertible when truncated, then there will be no ambiguity about which concepts and cases make up any sentence. But that still means that we need to construct a base matrix that is always invertible after truncation. It turns out that there are quite a lot of them, so let's pick one that has some particularly nice properties. What nice properties do we want our base matrix to have? Well, we want the base matrix to be dense, meaning that almost all of the entries are non-zero. This is so that a change in any concept leads to a change in almost all of the entries of the sentence vector. The other nice property to have, and this is more for aesthetic reasons, is for the inverse of the base matrix after truncation to be easily obtainable. It would be nice to be able to undiffuse the language easily, and the inverse matrix is most easily obtainable if it's simply the original truncated matrix itself. But notice that the truncation size is variable while we have a fixed base matrix. This means that every truncation to a leading principal submatrix of the base matrix must be self-inverse. We call matrices with this property leading self-inverse matrices. Since the language should allow for utterances of arbitrary length, we want to find leading self-inverse matrices of arbitrary size. We don't actually have to look very far to find one. The identity matrix is leading self-inverse, and so is its negative. But we want matrices that are dense, and it's not trivial to come up with dense leading self-inverse matrices. So, do dense leading self-inverse matrices even exist? Let's find out. It's not obvious how to construct such a matrix, so let's start small and see what we can learn from trying things out. If we truncate the base matrix to just a 1x1 matrix so that only the top left entry is left, then for it to be self-inverse, it can only be simply 1 or -1. Let's pick 1 for the top left entry. Now let's try to expand it into a 2x2 self-inverse matrix. Crucially, if we keep the top left 1x1 submatrix untouched, we can ensure that the truncated 1x1 matrix is still self-inverse. At the same time, we try to fill out the rest of the 2x2 matrix so that it is also self-inverse. Let's label the 3 unknown entries. B is the entry in the top right, C is the entry in the bottom left, and D is the entry in the bottom right. Since we want it to be self-inverse, multiplying it by itself should give the identity matrix. If we do so, the product we get has 1 plus BC in the top left, B plus BD in the top right, C plus CD in the bottom left, and BC plus D squared in the bottom right. We want this to be equal to the identity matrix. This gives us 4 equations, so let's see if we can solve this system of equations to find the values of the unknown entries. Let's look at the top left entry. It's equal to 1 plus BC, and we want this to be equal to 1. This means that B or C has to equal 0, or both. Now onto the top right entry. It's equal to B plus BD, which we can factor into B times 1 plus D. And we want this to be equal to 0. This means that, again, B is 0 or D is -1, or both. Because of symmetry, we get something analogous for the bottom left entry. C is 0 or D is -1. Lastly, the bottom right entry of the product is BC plus D squared, and we want this to equal 1. Earlier, we already found that BC must equal to 0, so this is simply D squared equals 1. In other words, D is 1 or -1. So now we have a few choices to make. Let's first try setting D to 1. Then, by the conditions imposed by the top right and bottom left entries, B and C would both be 0. What we then get is the matrix 1, 0, 0, 1, which is just the identity matrix. That's not very interesting. So let's try setting D to -1 instead. In this case, the top right and bottom left conditions are already satisfied, so we just need at least one of B and C to be 0. Let's say we pick C to be 0. Then, in fact, having any integer for B would give us a leading self-inverse 2x2 matrix.
In fact, we can use the same technique to expand the matrix to size 3x3, 4x4, and so on. At iteration m, let's say we want to expand it into an m by m leading self-inverse matrix, AM. The superscript denotes the iteration number. We have an m-1 by m-1 leading self-inverse matrix, AM-1. Then AM would look like this, where BM and CM are unknown vectors and DM is an unknown integer. Like in the 2x2 case where we multiply the 2x2 matrix by itself to get a system of equations that the unknown variables have to satisfy. Here, we multiply AM by itself and set it equal to the identity matrix. We get 4 equations as before.
Similar to the 2x2 case, from the first equation, we get that BM or CM has to be the 0 vector. Then from the last equation, DM must be equal to plus or minus 1. Now, let's say we choose C to be equal to 0. Then B just needs to satisfy the equation AB equals to -DB. This asks to find a non-zero B such that the matrix vector product AB is just a scaled version of B, where the scale factor is -D. It turns out that this is possible, provided that in previous iterations we have chosen a D that has the opposite sign of DM in the current iteration. The more such Ds, the more freedom we have in choosing B. This suggests that a good idea would be to alternate the sign of D between iterations.
So with this choice of D, out of B and C, we have quite a bit of freedom in choosing one of them, while the other has to be 0. Through this, we can extend an m-1 by m-1 leading self-inverse matrix into an m by m leading self-inverse matrix.
Since this process works for all positive integers m, we're able to construct arbitrarily large leading self-inverse matrices. There is, however, one problem. We're interested in leading self-inverse matrices because we want to use them to construct our diffuse Conlang, and for that, we need the matrix to be dense, or else the concepts will not be diffused across the whole utterance.
However, from our construction, we found that each time we expand the matrix, either B or C has to be completely zero. This means that at the very least, around half of the entries of the matrix have to be zero. That's not very dense.
So a dense leading self-inverse matrix does not exist. This is very unfortunate. But we still do have to come up with a dense matrix as the base matrix of our Conlang. What we can do is, instead of the base matrix being just a leading self-inverse matrix, we have it be a leading self-inverse matrix times its transpose, the matrix flipped across its diagonal. This way, the base matrix can be made dense and it will still be easy to invert any truncated matrix. If A is a self-inverse matrix, then the inverse of A transpose A is simply A transpose. Remember, our goal is just to have the base matrix be easily invertible. We'll also multiply it by -1 just to spice things up. So M is equal to -A transpose A for some leading self-inverse matrix A. So let's decide on a matrix A. For simplicity, each time we expand the matrix, we'll always choose C to be the zero vector, and D will alternate between +1 and -1, starting with +1.
Now, we just need to find what the resulting leading self-inverse matrix A would be. It turns out that we can indeed find a closed form expression for A is equal to D plus D times B times the inverse of I minus 2 inverse B, where D is the diagonal matrix with alternating +1 and -1 on the diagonal, and I is the identity matrix. The derivation is on the screen if you want to take a look at it. The matrix B in this equation is what we can use to choose the values of B in each iteration. We are free to choose any integer for each of the marked entries of B, and A will still be leading self-inverse. For our base matrix, we'll simply set all of these entries to be 1. And what does A look like then? Well, it looks like this. And if we multiply A transpose with A and take the negative, then we get the base matrix, which is indeed quite dense. So now we can finally start constructing our language.
To recap what we've done in the previous sections, our idea for a cursed Conlang is to have each concept in the language be diffused throughout the entire utterance. To achieve this, we needed to construct a base matrix, which is an infinite matrix over integers modulo p. A property we needed to have is that we can systematically truncate it such that the truncated matrix is guaranteed to be invertible. By using generalized results from linear algebra, it turned out that such a matrix is possible if we always truncate it into a square matrix and the modulus p is a prime number. We then tried to construct a base matrix that is dense and has the property that I called leading self-inverse, which will make it very easy to invert. It turned out to be impossible to make it dense, so we settled with a base matrix that is a product of a leading self-inverse matrix with a flipped version of itself. What we need to do left is to fill in the phonology, vocabulary, and grammar of our Conlang. But before that, we have to first talk a bit about history. The Tang Empire, which spanned much of modern-day China, was at its peak in around the 8th century, and it had a huge cultural influence on all of East Asia. This influence, of course, extends also to the language, Late Middle Chinese, which was the language spoken at the time in its capital, Jiang'an. The literary language of classical Chinese, read using Middle Chinese pronunciations, spread across East Asia, becoming the lingua franca of the region and loaning large amounts of vocabulary into nearby languages such as Early Middle Japanese, Middle Korean, Old Vietnamese, and other contemporary Sinitic languages. However, it's a little known fact that the influence of Middle Chinese was able to spread through time and space all the way to northwestern Europe well into the 20th century. One of the languages most heavily influenced is Dutch, which has an estimated 50% of vocabulary borrowed from Middle Chinese, comparable to Japanese and Korean. For example, one such loan is the word schwesschok, meaning mathematics, which displays the native word wiskunde. So why am I telling you all of this? Well, that's because we'll be using Sino-Dutch readings of early Middle Chinese syllables as the syllables of our Conlang.
Because Middle Chinese has strict phonotactics, the phonology of Goptjaam will be given by the correspondences to the initials, finals, and tones of the syllables of early Middle Chinese. Middle Chinese syllables are given using the Baxter-Sagak transcription. So here are the Sino-Dutch pronunciations of the 37 initials. Pa pa ba ma da 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 na tra tra dra na cha cha za sa za cha cha ja sha ja cha cha ja sha ja nya ka 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 nya ha ha ya la, and the 102 finals. A va ya va a va ya u ye ve ai vai a ve. You can read it yourself. There are also 4 tones. However, since Dutch is non-tonal, they have undergone various changes. The level tone became a non-stressed syllable in Dutch, Kjaangs. The rising tone became a stressed syllable, denoted with acute accents, bij. The departing tone in Dutch is not a tone, rather it became an S, jijs. And the check tone is also not a tone, but it makes the final consonant avoid the stop, nwat. The mapping between numbers and syllables will be done with the help of the Guangyun, a rhyme dictionary of early Middle Chinese published in the year 1008. If we have a number n, then we map it to the nth syllable that appears in the Guangyun. However, there are only 3,874 syllables in the Guangyun, which is not a prime number. The next prime number is 3,877. Fortunately, in this CSV file of Guangyun syllables I found, there are 3 extra syllables for a few readings not in the Guangyun. So, numbers 1 to 3874 will map to syllables in the Guangyun, and the extra syllables will correspond to numbers 0, 3875, and 3876. Furthermore, since Classical Chinese has a morpheme to syllable ratio of around 1, the vocabulary can also be derived from Classical Chinese. We simply do the reverse. For each concept, we find a Han character with that meaning in Classical Chinese, and see which place its pronunciation comes in the Guangyun, and that is its concept number. This also means that early Middle Chinese homophones will have the same concept number, and you're absolutely right. Now on to the grammar. Many theories of syntax use binary syntax trees to represent the structure of sentences, but since this language has no word order, that's not possible here. So what we'll be using is case trees, where each concept in a sentence is placed on the node of a binary tree. There are 4 main rules. First, to have a concept modify another concept, place the modifier on the child node of the modified concept. You might call this head-up case order. By default, what this conveys is that the head concept is related to the modifier concept, so any concept can be a child of any other concept. For verbs, arguments of a verb are treated as modifiers of the verb, so they're placed in the child nodes of the verb node. Second, if we want there to be more than 2 modifiers, we place a node concept with constant number 0 onto a child node, and then put modifiers on the child nodes of the node concept. This can be repeated to fit more modifiers. Third, for transitive verbs, the argument placed on the left child node is generally the agent and the right child node is the patient. So for the example sentence, the cat eats the fish, eat is on the top, cat is on the left, and fish is on the right. Arguments can be dropped if you don't feel like saying them. For ditransitive verbs like I give a fish to the cat, the order of the child concepts from left to right will be I, the donor, fish, the theme, then cat, the recipient. For causal concepts such as because and according to, causality goes from the left child to the right child. Fourth, relative clauses can be created with the help of a relativizer concept, which has concept number -1 and is denoted by a triangle. This is best explained with an example. If we have the cat eats the fish, then the phrase the cat that eats the fish would be this. Cat is in the parent node, and the cat eats the fish is a child tree, but with cat replaced with the relativizer concept. Similarly, the tree for the fish that the cat eats will look like this. You can also have the eating that the cat did to the fish, which would look like this. Okay, now let's say we have a tree of concepts, but where does case come in? Well, here's the fun part. We label the nodes of the tree with case numbers, starting from case number 1 for the root node, then layer by layer, we incrementally label the nodes from left to right, including null and unused nodes. This is done until all concepts have been labeled and we get a concept case pair for each node. This procedure guarantees that there are no repeat case numbers, and it's possible to reconstruct the case tree just from the concept case pairs. An equivalent procedure is to start with case 1 for the root node, and for each occupied node, if the node has case number n, then label its left child as 2n and its right child 2n plus 1. I find that this tends to be easier to execute. So, to translate into the language, we represent ideas using a binary case tree. And with the node labeling procedure, we get the concept case pairs. From that, we construct the summary vector and multiply it by the base matrix to get the sentence vector. We can then convert it into Middle Chinese syllables using the Guangyun. These are written in their Dutch orthography, or with Han characters, and we pronounce them using their Sino-Dutch pronunciations. The whole process can be reversed to translate out of the language. To automate part of this process, I wrote a Python script to convert between concept case pairs and the corresponding syllables in Dutch orthography and an IPA. This can be found in the Git repo linked in the description. So now if I enter the endonym of Middle Chinese, what I get out is Goptjaam, which is the name of the language. Now let's see just how cursed this language is. Keep in mind that the language itself only consists of the Sino-Dutch pronunciations and the 2 writing systems. Everything else is just for constructing the language. So first, a demonstration of the language. The example sentence, according to the laws of aviation, bees are able to fly, translated into Goptjaam is Jy skals gras dwy, jus sig miaus. If we change bees to birds, we get instead Deng mais biesvis gwok juksi. Because of the fusion, every syllable is different between the 2 sentences. Conversely, if we mispronounce the sentence, say we pronounce the last syllable miaus with a level tone meow, then it becomes something along the lines of the witty and deep sickle kneels in warm milk running frantically. Okay, let's look at another sentence. Its fat little body gets off the ground. If we want to say this after our first sentence, we don't simply say the 2 sentences one after another. Rather, we connect the case trees of the 2 sentences together into a single case tree, and we get this. For, according to the laws of aviation, bees are able to fly. Its fat little body gets off the ground. This is again completely different from saying the 2 sentences separately. There are 2 things at play here. 1, by combining the case trees, the case of each concept is changed. And 2, because of diffusion, each concept is diffused across all of the syllables and utterance. Because of the grammar of the language, all concepts have cases, even verbs and grammatical words. Case in this language functions more like word order in natural human languages. Some more consequences of the language being diffuse. 1, it's not really glossable. Like in the utterances earlier, if you just look at a single syllable, it's hard to even fathom what it means. Which is not to say it doesn't convey information, it certainly does, but I'm just unable to wrap my head around what information it conveys. It's like asking what the phoneme H means in English. It certainly conveys some information, but it's very, very hard to describe it. A consequence of this is that you can't really make a dictionary between this language and a natural human language in the sense of mapping between finitely sized concatenations of phonemes. The best you can do to get a finitely sized dictionary is to map morphemes to concept numbers, provide a formula for the base matrix, and provide a conversion chart from syllable numbers to syllables. Furthermore, I'm not even sure how to analyze the morphemes in this language. You can either think of each syllable as a morpheme, whose meaning is almost impossible to represent in English, or you can think of each morpheme as an infinitely long array of underlying phonemes with incredibly complicated rules for combining phonemes from different morphemes into the resulting phonetic realizations. But enough of that. It's time for what you've all been waiting for. The opening lines of the B movie in Goptjaam. Bij Kjaang tron wat jij zag weer, Byung kwe nep noen zee steek koei. Byung von gons west jouw dong trap. Zwak zien truw gwangs goos baasjes. Zemstje geert geen mok geweest koek. Trin wen jies trouw li sing gwak. Nee schus jouw shams jouw nou weer. I'm Kat, and thanks for watching.